Let me start by just saying, for those of you that have any kind of a fear of standing up in front of groups of people and talking, I find this about 10 times more difficult to sit in front of a laptop and try to record a lecture. It's very, very awkward, but in any case, bear with me as I try to go through this. In any case, this is the 5th lecture in X-ray diffraction. So we'll kind of pick up where we left off last time. Some of this stuff we already talked about informally, but I guess the slides kind of formalize it. These are XRD loose ends. So we'll talk a little bit about sample preparation, powder mounting, the importance of sample size and thickness, the effects of sample preparation, and we'll talk a little bit toward the end about the effect of a diffracted beam monochromator. We'll also talk about optimizing test conditions for obtaining diffraction patterns. That means like the step size, the length of time that you run the scan, and so forth. And then we'll talk about some common data processing. I'll skip the slide. All right, basic sample prep. Sample preparation is often required to reduce the grain size. We've talked in the past about grain size effects and preferred orientation. There is actually an optimal grain size. Reducing the grain size at the same time also improves uniformity or homogeneity of your sample. You definitely want to make sure your sample is thoroughly mixed. Potential problem areas that come as a result of this, as we've discussed over and over again, it may generate preferred orientation if the sample is not prepared properly. And then another thing you need to be aware of, very, very intensive grinding or very intensive processing can lead to phase transformations if you're generating a lot of heat or imparting a lot of energy into the sample while you're preparing it. This is especially true when dealing with organic materials. Pharmaceuticals in particular, you really want to try to avoid grinding. Obviously in ceramics and well, metals you can't really grind, but in ceramics, that probably isn't too much of an issue. And then we'll talk about the general techniques of sample prep, front loading, rear loading. I don't recall actually having a side loading slide in here, but we'll see when you get there. And then a smear mount. So powder requirements. At a minimum, the powder size should be able to pass through a 325 mesh sieve, which is a sieve that has an opening of 45 microns. So that would make sure that no particle is larger than that. So if you don't have access to grinding equipment and you just want to make sure you have a reasonable particle size, if it passes through that 325 mesh sieve, it is a way to at least get to some sort of bare minimum. You can see from the slide that the optimal grain size is actually somewhere between about 1/2 and 10 microns. Over here on the right side is a plot based on this relationship up here, which is the number of particles equals this constant times the size of the sample holder divided by the diameter of the particle cubed. Obviously, the larger the sample holder, the more particles you'll get in there. I'm not really sure what they use for samples or sample holder size to generate this particular graph, but I think the point of the graph is fairly obvious. If you look at the 45 micron position on here, somewhere in here, you're generating, about 100,000 particles. All right. Once you get down to that 10 micron range, down to 1/2 micron, of course, you're, 10 to the 7th, 10 to the 8th, 10 to the 9th, and so forth. By the time you get to that 1/2 micron, you're at sort of 10 to the 10 number of particles in your sample, which is, more grains to actually be in the reflecting position. So it gives you a complete pattern. So hopefully, if you don't have a reason to have preferred orientation, i.e. the shape of the particles or something, you at least have enough particles that you should get a reasonable pattern out of it. The basic tools for particle size reduction. On the upper left there is a standard mortar and pestle that happens to be agate. I think just about anybody working in X-ray diffraction has one of these. For the most part, something like this will be fine for soft materials. But as you get into harder and harder materials, you might need harder materials to actually break it up. Some common media for breaking up samples is agate. That's probably the most common in terms of a mortar and pestle. Al2O3 or corundum is another common one. Zirconia, also common. And then about the hardest, easily accessible media for grinding up materials is tungsten carbide. You aren't going to have something like a tungsten carbide mortar and pestle. They do actually make mortar and pestles out of alumina and out of zirconia. They get, considered they're quite expensive, but these are available. You can hand grind when you have soft materials or small amounts. Obviously, if you have large amounts, you can rely on mechanical milling. Over here, shown on the right-hand side, are ball mills. This is what I use in my lab the most, as long as there's sufficient sample material. For the most part, I always use tungsten carbide. Why? Because it's the hardest of the things in that list, and so for the most part it will break up just about anything. The one thing I will have to warn you about, though, tungsten carbide tends to contaminate samples quite a bit. All of these have the potential to contaminate. If you actually go to somebody's website that supplies this type of stuff, they will actually, for each of these types of milling media, discuss hardness versus wear resistant. And just because something is hard does not mean that it's not wear resistant. And in fact, tungsten carbide tends to wear a lot, where agate does not tend to wear a lot, although tungsten carbide is considerably harder than agate. So the point being is tungsten carbide is a very good milling media, but it does tend to contaminate quite a bit. Fortunately, in X-ray diffraction, the contamination is at such a low level that you really tend to not see it unless you're doing a lot of milling. When you place the powder into the mount, you want to do anything you can to avoid preferred orientation. Again, we've discussed this a lot of times. The two little cartoons on this slide are just kind of showing what preferred orientation is. I think we all saw that in the SEM when we looked at the gypsum. They look like, sort of like sticks or pieces of lumber, and they have a propensity to sort of lay down in an oriented manner. In these particular cartoons, these arrows are just showing sort of an axis or direction of the crystal. In the image on the left, it's basically showing that it's completely flat. Clays tend to do this. So if you're doing X-ray diffraction on a clay, they kind of have a platelet shape to them, and so they'll lay down flat like that image on the left. And the image on the right is what you might get from rods and sticks, something that's sort of acicular in terms of shape. But anyway, we need to try to avoid and do what we can to avoid preferred orientation. When we do pack our powder into the sample holders, we want to obtain a smooth surface on the top. All right, ideally that surface would be in the same plane as the eccentric plane of the diffractometer, so that the peaks are in the right position in the diffractogram. And then you want to obtain a high packing density in the sample holder. The more material that you actually pack into the sample holder, the more grains you will have to diffract, and the more intense your X-ray diffraction pattern will be. Okay, the most common technique, this slide is actually kind of old at this point. Front loading is actually not the most common technique. Back loading is the most common technique now. This is actually a slide from the days when they actually had the sample holder would just fit directly in there. It was nothing but a plate with a cylindrical well in it. But what you would do is basically fill this well with your powder and then use something flat like a glass slide or a razor blade to scrape off the top of it. So you'd fill some powder in it, you'd tamp it down a little bit with something, you'd put a little bit more powder in it. This is to increase the packing density. And then, like I said, like I showed in the bottom of the slide, you would use a razor blade or a glass slide and then smooth out the top surface. An obvious problem that can come from this technique, which is really why it's kind of been abandoned in favor of back mounting or back loading, is that when you drag that razor blade or glass slide across the surface of the powder, you actually will have a propensity to orient it if it has something in its shape which would allow it to do it. And again, if you take the gypsum that we looked at in the SEM, that's a good example. If you were to fill this in it, it might actually be somewhat randomly oriented as you just drop it into the well of the holder. But then once you drag something across the surface, you're going to actually, one, not only flatten out the top of that surface, but potentially even orient them in the same direction. Which will just exacerbate any preferred orientation that you have. The next slide. Okay, front loading with a solvent. This is useful when powders are not manageable. Sometimes powders can actually be of such a small particle size and have such a low density that they stick to things. They may even waft around as you're trying to load it in there. Static charge can cause them to stick to, the glass slide as you try to put it in the sample holder. When you remove the glass slide, static charge can cause the powders to actually stick to it. So one thing you can actually do is use a little bit of a solvent. Typically an alcohol is best, not something that could conceivably change the phase of the sample. So in my lab, I would use like methanol, maybe some isopropanol, and you would mix the powder with a little bit of the solvent. You load it from the top side, you press it in there, and then you let the solvent evaporate and the powder will lightly agglomerate and it will stick to the holder. So this is another method for doing tricky samples. Obviously, you could do the same backloading too. Backloading, I brought in an example of how that works and showed that in class. Basically, it's just the opposite. The cylindrical well in the sample holder goes all the way through. So you put the sample holder down on something flat, you load it from the back, you tamp it down, and then you flip the sample over. And then it would go in the instrument like that. Obviously, this avoids the problems of doctor blading the top of a front-loaded sample holder, and hopefully avoid some of the preferred orientation problems. Dusting onto a glass slide. This is used when a sample has really, really low absorption. The sample holder is usually just a glass slide with a little bit of petroleum jelly. This can also be used when you don't have a lot of sample material. All right, you would take a glass slide and you would just smear some petroleum jelly across it, and very, very little. You don't need a lot. You don't want to goo it up. And then you just sprinkle some of your sample right onto the Vaseline. I think I brought in a better holder is actually a zero background material. If you use a glass slide, you are going to get an amorphous hump in your X-ray diffraction pattern from the glass. It'll characteristically be at about 22.5 degrees. So you'll get that broad amorphous hump, which again, I think we talked about in class. A better holder is a zero background material. The most common zero background material being a single crystal silicon plate. And what they do is they take the single crystal and they cut it just off axis. And then that way there's nothing that would ever be in a reflecting or diffracting position from the silicon. They refer to it as a zero background holder. It's not really zero background, it's low background. But the benefit of it is that it doesn't have any diffracting planes, so it won't put any peaks in your pattern. Issues related to sample size. When the divergent slit is fixed, the incident beam can become larger than the sample at small angles. All right, and the diagram up there sort of demonstrates this. You have the beam source, and you can see that it diverges onto the sample. At low angles, the size of that beam is going to be can be very, very broad. Using the relationships given on the slide, and based on the size of the divergent slit in the diffractometer, you can actually calculate how wide the beam will be at various angles. The importance of this is that at very low angles, the beam is probably going to be off the sample and hitting the actual sample holder itself, which will result in background. So you'll get some scattering from the sample holder. You might want to ask the question, why do you not get diffraction from the sample holder? Most of the sample holders are made now of stainless steel, and that's because at those very low angles, the steel actually doesn't have any diffracting planes. As the angle goes up and is high enough, then the beam becomes small enough that it just hits the sample itself. Just as an aside, obviously you can correct this by using a smaller and smaller divergent slit. And you can definitely go sufficiently small that it will always be on the sample in its entirety. However, if you reduce the size of the divergent slit, you're going to reduce the intensity of the overall diffraction pattern. Sample displacement errors. I believe we talked about this in class a little bit, A sample displacement error is when the sample sits slightly above or slightly below the eccentric plane of the diffractometer, or that optical axis plane in the diagram. That would be the dotted line going straight across the circle. And then you can see that you can displace that sample by some amount S. Okay? What that will cause the pattern to do is shift by some amount in degrees, which can be calculated by the relationship on the right. So delta theta equals S cosine theta over R, where R is the goniometer radius. Okay? So you can actually, and obviously this is a function of the cosine of the angle, so it does vary by the 2 theta value. But, you know, simply put, if your sample is above that optic axis, you're going to shift your pattern to the right. If it sits below, you're going to shift your pattern to the left. And then this diagram or graph on the lower right side basically shows what the displacement would be for various values of S from minus 0.05 millimeters all the way up to 0.2 millimeters positive, that displacement as a function of the Bragg angle theta. You'll see that they converge at 0 at 90 degrees, which of course would be where both the beam and detector were both directly, 90 degrees. They would be directly over the sample. So sample displacement goes away as you get closer and closer to 90 degrees, which is kind of an obvious thing. When I talked a little bit about Rietveld last time, I mentioned that your peak position is also a function of the d-spacing or the lattice parameters of your sample, which is also a function of 2 theta. Fortunately, those functions are different and can be decoupled by a Rietveld refinement. So fortunately with computers today, you can actually identify and separate any change in the diffraction pattern that's a result of sample displacement or a result of differences in lattice parameters. The need for a small grain size. Again, we've talked about this a couple of times sort of informally. When the grain size is quite large, this is also the case if you have too few particles in your sample also. The Debye rings are spotty. And if you look down here at the film shown on the bottom of the slide, you will see that those rings are incomplete in several of them. And in some you could even see where they are dots. If you sort of zoom into those rings and look at them closely and look at different paths that you might take, because if you recall, I mentioned that the diffraction pattern is basically a slice out of this film. And depending on where you slice it, you could get differences in intensity. So in the case of reading 1 on the slide, is following this path, right? And in this particular position, we happen to have complete blockage or a high intensity. So this would be an example of a peak that would be very strong. As we go down, pardon my drawing, in this position, you didn't have a particle diffracting, right? So it would be weak, which is obviously what the W is. And we keep going, weak. And here it's partially blocked, so you'll get a moderate intensity peak. Alternatively, if we follow a different path down here, that same peak, which was very strong in one path, would be very weak in this path. This one, which was previously weak, now is strong. This one was weak, but here it's moderate. And in this one, it's weak. So this is why you want small grain sizes, because large grain sizes tend to result in these spots in the Debye rings and result in variations in intensity that are not what you would expect for a completely random powder sample with an infinite number of particles making the rings. And how the effect of a large grain size manifests itself is sort of shown in this diffractogram. It results in erratic intensity swings. So the actual blue plot down below is actually from a Rietveld refinement, all right? And that's showing what we would have expected the peak intensities to be for this lanthanum tin hydroxide. And then you can see the actual experimental pattern, which is represented by the red dots, is unusually high. Like so. All right, that's how a large grain will manifest itself in a diffraction pattern. So if you have a phase and you know what it is and you obtain a diffraction pattern and you get some very, very strong peaks where you don't expect them, that basically means you probably have a grain size effect and that you need to reduce the particle size of your sample. Optimizing test conditions. All right, brief overview of what we'll talk about: wavelength selection, use of a diffracted beam monochromator, incident beam aperture, diffracted beam aperture, the power setting, step size, counting time, scan range, and quality of the test results desired. All right, these can all affect the quality of the diffractogram you get, depending on your objectives. Time, of course, is always important, so you want to balance out the quality of your scan with the amount of time that it takes to obtain the scan. The wavelength selection, all right, for the most part, you will find 90–95% of the diffractometers in the world use a copper anode, a copper tube. By and large, you don't really have a choice in what wavelength you have. You're kind of limited to what the lab happens to have in place. The diffractometer downstairs in CCR uses a copper tube, and like I said, that's the most common for a lot of reasons. There are many alternative anode materials: titanium, vanadium, chrome, manganese, iron, blah, blah, blah. You can actually read the list. I would say probably the second most common anode material would be chrome. So if there is a common alternative, that is it. Okay. It actually does improve the resolution somewhat due to the larger wavelength. All right. If we were sitting in the middle of class, I would ask the class, what would this do to the diffraction pattern if you use a larger wavelength? And the answer to that question is it would stretch out the pattern itself, right? The peaks, it ends up making the peaks spaced out farther apart, all right? The peak breadth is a function of the particle size, the sample itself, and the optics of the instrument. So the peak breadth won't change as a function of the anode material, but the larger wavelength will cause the pattern to stretch out a little bit and might deconvolute some of the peaks that might appear overlapped using a copper tube. All right, that might bring an obvious question as to why you wouldn't then just use a chrome tube. Chrome tubes actually have substantially lower intensity than copper due to the fluorescence yield and lower power of the tube itself. Copper is a very good conductor of heat, so you can actually operate it at a higher voltage and higher current level. Chrome is not a good conductor of heat, so if you operate it at too high a current and accelerating voltage, you'll tend to overheat the tube and burn out the tube quicker. The other problem with the chrome tube is because it does stretch out the pattern. If you're relying on some of the higher 2 theta values for some type of an analysis, like a stress strain analysis, which we didn't really talk about, it can actually push some of the 2 theta values out past your ability to actually measure them. The other thing that chrome is often used for is it has a K alpha energy of about 5.4 keV, which will eliminate iron fluorescence. Obviously, you could go look at absorption edge and X-ray energy information and figure out that there are also some elements, though, that would fluoresce in the presence of a chrome tube. So you have to consider all of these things. I think for the most part, most of you don't really need to worry about it. Copper is what's available. It's just you would want to be aware that there are alternatives and understand what those alternatives mean or don't mean. Another way to deal with fluorescence is through the use of a diffracted beam monochromator. A diffracted beam monochromator is actually a graphite crystal, which set in a certain position will only allow certain wavelengths to pass through it, right? So this is used to remove the unwanted radiation that contributes to a high background. It's very effective in removing that background. The only difficulty with it is that it actually reduces the intensity by half. So it's a trade-off. I think we discussed this in class a couple of times. I have one in my lab. I really don't use it very often. I actually just tend to run scans that fluoresce a lot longer, and then I just manually remove the background or reduce the background so it looks better. But either way is an acceptable way of dealing with fluorescence. Obviously, the other way, as we just discussed on the previous slide, is if you have access to a chrome tube, that would be a way of avoiding fluorescence, at least from iron. We'll talk a little bit about the incident beam aperture. It's sometimes referred to as the divergent slit. All right, it has the largest effect of it is on the beam size itself. This is the first slit that the beam will go through out of the X-ray tube. You want to try to match that slit more or less to the sample size. I think for the most part, most people use about a 1/2 degree divergent slit. That's kind of the standard optics for most diffractometers. The diffractometer in the first floor of CCR is probably set up in a standard configuration where it has a 1/2 degree divergent slit. Going larger is probably going to accomplish not much, except causing your peaks to start to broaden, and you'll have a lot more spillover on the sample holder, so your background will go up. Reducing it will actually reduce some of that background in the low end, low 2 theta portion of the diffraction scan, but it will also reduce the intensity, sort of as the bullets say. So it has a large effect on the beam size. It has little effect on the system resolution. It does have some effect, but it has a large effect on intensity. And then, of course, the plots that we have here are plots of, what do we have here? The first one on the left side, the divergent slit aperture in degrees. And on the y-axis, we have the normalized integrated intensity. So you can basically see that as you go to a larger and larger slit, you start to maximize your intensity, but then you reach a point where it doesn't really go up a lot more. So there's kind of becomes diminishing returns by going to a larger and larger slit. I would say most people probably are using a 1/2 degree, maybe 1 degree. You can sort of see that using a 1/2 degree slit gets you kind of 70% of the required intensity while still maintaining good optics. If you go to the graph on the right side, we have the divergent slit aperture on the x-axis, and on the y-axis is the average full width half maximum of the peak. All right, so this is giving you an idea of how broad your peaks are as a function of the divergent slit aperture. And you see the same kind of trend. You get some peak broadening as you go up to about 1 degree. And then it kind of flattens off where it has little or no effect. So once again, you can kind of see that, you know, the 1/2 degree range sort of puts you in a full width half max of about 0.07 to 0.08 degrees. Not a significant effect. And that's kind of the point on the left where it says little effect on system resolution. But this is what the divergent beam or incident beam aperture does. The diffracted beam aperture, which is on the other side, so this is after the beam has hit the sample and diffracted. It has the largest effect on resolution and a large effect on intensity. Again, the same type of plots. On the left, we have the x-axis is the receiving slit aperture. All right. And on the y-axis, we see the normalized intensity. And same kind of rough position. We tend to try to target being in this area, all right, in terms of intensity. Going over to the plot on the right, you see again, the receiving slit aperture size is on the x-axis and the full width half maximum is on the y-axis. And you can see that there's pretty much a linear relationship between the peak breadth and the receiving slit aperture. So you want to try to keep the receiving slit aperture relatively small. The power settings of the X-ray tube. This is one way you can improve the intensity of your sample or of your diffraction pattern from your sample. The intensity of the X-ray beam is proportional to the voltage to the 1.5 power, all right? So you get, more than a 1-to-1 bump by turning up the voltage. The intensity of the X-ray beam is directly proportional to the filament current. This obviously begs the question, why not just run the accelerating voltage as high as you can? And the answer to that is because you will ultimately burn out the tube faster if it can't dissipate the heat fast enough. Typical settings for a copper tube are between 40 and 40 kV, 40 and 45 kV for the accelerating voltage, and 20 to 40 milliamps, depending on the tube power. Downstairs in the diffractometer and CCR, this typical run is 45 kV and 40 MA. The power is usually set at about 70% of the tube rating in terms of the combination of those. That tube downstairs will actually operate at 50 kV, but they don't recommend doing it. The step size. I'm not really sure what that first bullet means. Step size used for step scans. The step size is how the diffractometer, the goniometer actually moves as it scans through the 2 theta. All right, so that is, done in degrees. All right, the optimal step size is really dependent on the sample itself and the peak breadth of the resulting diffractogram. All right, you want an optimal step size where the full width is somewhere between, or the step size is approximately the full width half maximum of your peaks divided by 5 to that number divided by 7. Because of the kind of detector that you have in the diffractometer downstairs, your step size is actually a function of the detector itself and the stepper motor in the diffractometer. It actually operates, I believe, the step size is an integer multiple of 0.008 degrees. So you'd have 0.008, 0.016, and so forth. Smaller step sizes are used for high resolution work, such as quantitative analysis, and a larger step size can be used for quick scans or just doing basic phase ID. Another way to think of this optimal step size is to think of the number of data points that you have in your full width half maximum. If we were to draw a peak, and here again I'm going to do my really bad artistry. Oh, that actually didn't come out too bad, right? So we have a full width half max in here. So that's your full width half max of your peak. This optimal step size, the other way to think of it, is the number of data points that you're going to have in your full width half max. And in general, you want at least 5 or 6 data points in the upper full width half maximum of your peak, so that your peak, for lack of a better scientific term, looks peaky, right? If you have too few data points, you won't necessarily hit the real peak summit, all right, or the real peak position. So you want to have enough data points that you can actually define that peak shape. And so optimally, you would like to have sort of 5 or 6 data points in your full width half max. All right, I drew 5 in there, but you get the idea. If your step size is too large, right, you effectively could just be drawing a triangle in the top part of that peak, and depending on where you happen to be in those step positions, you could actually be missing the actual summit of the peak position. All right, so a better way to look at it is not full width half max divided by 5, but run a quick scan of your sample, zoom in on a peak, and actually look at the number of data points in the peak and make sure that the peak is being defined properly. So that's the importance of step size. The counting time is an important aspect to obtaining a good diffraction pattern. Simply put, the longer you run your scans for, the better your pattern will be, but obviously there becomes a point at which scans can become ridiculously long. Most people are in a hurry. So probably the best way to think about it is that the count time depends on the application that you're trying to do. And in general, it's kind of accepted that if you're doing Rietveld, precision lattice parameter work, any kind of quantitative analysis, you generally want to have at least 10,000 counts in your strongest peak in your pattern. If you're just doing basic phase ID, then you want to have 5,000 counts. And then if you're just doing a quick scan, you just want sufficient information on the pattern to kind of, help you understand whether the pattern is going to ultimately give you the information that you want or not. And you usually can get away with a couple thousand counts. When we set the counting time in a diffractometer, it's generally done in terms of a count time per step. All right. It should be noted that the modern diffractometer actually has what they refer to as a strip or linear detector, as opposed to the older diffractometers have a point detector. If you want to know how long your overall scan is going to take, you might, it should be relatively straightforward that if you were to take your count time in seconds per step, and let's just say as an example, we select 100 seconds a step, the total count time in the diffractometer might calculate out something like this. So if we have 100, second per step, times the range of your scan. Let's just say, for example, we decide to do a range of 80, from 5 to 80 degrees 2 theta. Right? So it's a 75-degree scan. And then you want to divide that by your step size. So let's say, for the sake of argument, we'll say a step size of 0.167, which is actually, I think, the standard setting down on the diffractometer downstairs. So if you go through that calculation right there, and 100 seconds a step is actually a pretty reasonable count time. If you actually go through that calculation, you'd pretty quickly see that it would calculate out to a ridiculous number of seconds. And by the way, this is in degrees per step. And of course, all the units properly, go away and leave you in terms of seconds. However, that formula would strictly be for a point detector. But the new modern detectors, like I said, are actually solid straight linear detectors that have multiple channels that actually collect multiple angles at once. The detector downstairs in CCR actually has 127 channels. So it actually has the ability to collect 127 angles all at one time. And then, of course, as it passes through each particular 2 theta position, you'll actually collect that 2 theta position 127 times. So if you want to know how long your scan will actually take, you would then divide this whole thing by 127. All right, and that gets you to a more reasonable number. So that's how long a scan would actually take. There's actually a little bit more to the calculation, but I'm not really going to go into it here. But that gives you, that's a rough approximation of how long the actual scan will take. The scan range should start a few degrees before the first peak. This is one of the reasons why it's a good idea to run a quick scan. In my lab, I run a quick scan that takes sort of 5 minutes, maybe 10 minutes at the most. All right. If it's a powder, or if the powder is unknown and you don't know and you don't want to run a quick scan, I generally start everything at 5 degrees. All right. The upper limit is really based on the application and the material response. A Rietveld refinement actually operates to above 100 degrees. However, it really, by the time you get out to 100 degrees, most of your peaks are starting to get low in intensity and very, very broad. And so the Rietveld refinement will actually go that far, but it probably won't affect the results of the refinement very much. Simple phase ID stops at about 60 to 80 degrees because your peaks start to repeat anyway, meaning you just get to higher order peaks. So as a general rule of thumb, I sort of tell people 5 to 80 or 90 degrees for most applications is a sufficient range, but it really depends on what you're doing. If you're dealing with organic molecules that have very, very large d-spacings, most of the pattern is going to be in the low 2 theta region. So you may actually need to start that at 2 or 3 degrees. And in fact, in the pharmaceuticals world, the accepted range for pharma, I'll just actually write it on here so you have it. sorry, yeah, try using my finger. Pharma operates kind of in the 3 to 50 degree range. If you're working with metals, the D-spacing in a metal is actually quite small, all right? So the majority of the peaks are actually pushed out farther to the right, the higher 2 theta values. So you may not need to start it. You could, some metals you could actually start at 20 degrees because there'll be no peaks below that. I think I mentioned earlier the stainless steel sample holders at the low angles they result in a high background, but they don't result in any diffraction peaks because there are no peaks at those locations where the beam is spilling off the sample and onto the sample holder. And you know, as I've kind of mentioned, best thing to do generally is to run a quick scan before you run your final scan and use that to decide the step size and the counting time. I think for the most part, the default settings on the diffractometer downstairs, which are, like I said, are 0.0167 degrees step size. And the ranges I've given here, sort of 5 to 80 degrees, are good enough for most applications. The time is something, though, that you really do need to think about and take advantage of. The longer the scan, the better. You'll improve the signal-to-noise ratio. Your limit of detection will go down. So, but you need to run the quick scan to assess that. So it all depends on the quality of the scan desired and needed. So here's an example. This is two scans, one at 0.15 degrees per minute and the other one at 12 degrees per minute. So 12 degrees per minute, it's very fast, right? So if you think about that, if we're going, you know, from 5 to 80 degrees, that's 75 degrees. You're going through that scan in a few minutes. Whereas if you're going 0.15 degrees, that's a full order of magnitude, 2 orders of magnitude slower. And you can see the difference in the resulting scan quality. And as I said on the previous couple of slides, it really depends on the application, whether it's good enough. That blue scan is probably sufficient for phase ID and might give you a rough idea of you know, what kind of scan you can obtain. But if you're interested in a high or a low limit of detection, so you're looking for a phase that might be there in a very small amount, you know, you need to run the scan long enough so that the signal to noise is sufficient that you can actually discern peaks. If you look down in this range, you'll see in the blue scan, there is what really looks like a peak, but it's really kind of hard to tell. And you just kind of have to stare at it. And, you know, if you're trying to figure out the exact position of that peak, it's difficult. Whereas in the red, you know, you can very clearly see those peaks. So if that was a phase of interest, you would need to run this scan long enough that you can make out the peaks properly. Some common data processing. Data, yeah, I don't really like the slide. It probably shouldn't say data must be pre-processed. Data can be pre-processed. Types of pre-processing include background subtraction, pattern smoothing, K-alpha 2 stripping, and then we can do some peak searching, and then you can do some profile fitting of overlapping peaks. The reason that I say data can be pre-processed, obviously peak searching and profile fitting doesn't change the data. In my lab, when I do a diffraction scan, I always provide my customers the raw diffraction scan. I don't like to manipulate the data, so I avoid doing that for, you know, unless it's absolutely necessary. So background fitting and subtraction. Most of the software packages that are available have some kind of a background fitting tool. All right. The physics of the background and the sources of the background is reasonably well understood, but I don't know that there's a really good model for it. Most of the packages just use some kind of like an algebraic, you know, an exponential fit, or a cubic spline, or some other, you know, method of fitting a background. You can see in the very top scan, you know, this background is being pulled up into the bottom of the peaks, and that's really not appropriate. The background tends to change smoothly across the 2 theta range. Most of the controls in the background fitting allow you to decide how many points to actually put in the background. The second one is a smoother background fit and probably more appropriate. In general, the background should go through the center of the noise in the troughs between the peaks. You can do this, using the algorithms built into the software, or you can fit the background manually. What I tend to do is let the software initially fit the background, and then I do a review of all the places where it's not smooth, and I tend to make manual adjustments so that it smoothly follows the bottom of the pattern. You do have to fit a background to it to do your analysis, but you do not have to subtract the background. Most software has the ability to actually subtract it. You will see that a lot of diffraction patterns, when they first come out of the diffractometer, tend to follow that kind of a shape, where you have a very high background in the low end of the 2 theta range. That's primarily scattering off the sample holder. Okay, a lot of people don't like that, so they will actually subtract the background to give sort of a flat diffraction pattern. And a lot of people do actually do this for papers, and it's certainly appropriate to do it for papers. But obviously you are actually, by removing the background, you are altering the actual raw data. But it is appropriate, to, like I said, to do that for papers and your theses and what have you. Smoothing is something that I try to avoid. If you really need to get rid of the noise in the pattern and you want to make it look better, and by the way, in these 2 patterns, the background has actually been subtracted, right? That's not a real background, so somebody's removed it. Most of the software packages actually include some kind of a smoothing method, which is averaging over a certain number of points. I would say 11 to 15 points is a reasonable number of data points to smooth over. You want to avoid smoothing peaks, but sometimes it's unavoidable. Obviously, if you smooth, you can disrupt some of the peak information when you're looking at very, very small amounts of something. So I do not tend to smooth my patterns ever. K-alpha-2 stripping. Stripping does introduce artifacts of its own. You can mathematically, deconvolute the peaks, because we know what the relative intensity of the K-alpha-2 peak is relative to the K-alpha-1 peak. But as you sort of zoom into this pattern, you can see where we strip the K-alpha-2, you get these artifacts in the bottom, right? It really should look like it does in the bottom, but you just need to be aware of that. Once again, I do not remove the K-alpha-2 peaks from my patterns. I'm aware that they're there. When I do peak picking, the peak picking will allow you to, check a setting, whether it should be aware that K-alpha-2 exists or doesn't exist. But if you need to remove the K-alpha-2, you can do it, but you do need to be careful using it. Peak search algorithms. Again, all the software packages have a peak search algorithm, which is where you can just basically tell the software to go off and locate all the peaks for you. All right. Most of them work using the second derivative. So they go through and they identify where there's a change in the slope, right? And you can see where the second derivative on the very bottom finds the center of the peak. All right, the second derivative method is pretty standard in all the peak searches. We don't really need to spend too much time talking about it. You guys can think through the math on your own, why looking at the derivative and the second derivative would be useful for identifying peaks. For what it's worth, let's see here, do I have a, yeah, okay, there's another slide. I usually use the peak picking algorithm built into the software, but then you have to go through it manually and either include, sometimes minor peaks are missed and you need to just put them in yourself, and then sometimes artifacts can show up as peaks that are not really peaks, and you'll have to go through and manually remove those. So always review, as it says here, this is important, always review machine generated peak searches. If you don't, you're asking for trouble. In the pharmaceuticals world, most pharma companies actually require a peak listing. You may not need to do this if you're doing inorganic work, but the pharma world actually relies on the peak locations for the identification of specific drugs. And if you just use a machine-generated peak search, you're very likely to pick up things that are not there and ignore things that are there. So you do need to manually review all peak picking processes. In summary, some sample prep is often required, right? You need to reduce the grain size to 325 mesh or better. To be honest, 325 mesh really isn't that good. You probably will have to do some grinding, but you want to minimize grinding if there's any risk of causing any kind of changing in the sample itself. This is especially true in organics and pharmaceuticals. You want to optimize test conditions by running a quick scan first, and then based on that quick scan, you can decide your scan range, your time per step, and the step size. For all practical purposes, the 0.0167 step size, which is kind of the default downstairs, is generally good enough for anything you do. There's really no purpose to go beneath it. And doubling that to 0.033 can actually create problems. So for the most part, 0167 is the right step size using the diffractometer downstairs. But the scan range and the scan time is something that you will want to base off of the quick scan. Massaging the data, processing data is often done. As I said, I don't, but you may need to for submissions to papers and whatnot. But as the second bullet indicates, show the raw data along with the process data to show that no artifacts have actually been introduced. So they can see the raw data and realize that you've just cleaned it up for presentation purposes. And that is the end of this module. Thank you.